A boat leaves the dock at 7 p.m. and travels due south at a speed of 20 kilometers per hour. So this is showing the path of that boat that left at 7. Another boat has been heading due east at 15 kilometers per hour and reaches the same dock at 8 p.m. So an hour later, this other boat reaches the dock. How many minutes after 7 were the two boats closest together? So we want to find when the distance was the smallest. That's what they're asking us when they say how many minutes after 7 were the two boats closest together. So we want to express this distance between the boats as a function of time since 7 o'clock then. So we want to find the time at which this distance is the smallest. So what do we know? We know the rate of change in position, or in other words, the speed of one boat is 20 kilometers per hour, and of the other is, the speed is 15, but notice that position is decreasing. In other words, his distance from the dock of this guy going east is decreasing. So we have this diagram I've already drawn, and it's helpful to draw that diagram because you're going to see that if you simplify it a bit, it's just a right triangle, and that distance is the hypotenuse. So we'll use that to figure out this distance in terms of time, in terms of these rates. So that since we were told that the boat A is traveling at 20 kilometers per hour, its rate of change is 20 times t, if I let t be my number of hours since 7. And by the way, I'm making t hours because my rates were in kilometers per hour. So I'm going to change at the end to minutes. And then the distance that B is from the dock, now that distance is decreasing, is this expression 15 minus 15t. So I got that because I was told that B is headed due east at 15 kilometers per hour, so that's a constant rate. So B, the position is changing in a linear fashion. So in other words, I have a line, and its slope is minus 15. And I also know that after 1 hour, it's 0 kilometers from the dock, so I have that point on the line, 1, 0. So using that information, I get this equation of the line. This is the equation for B's position at time t relative to the dock. So then I want to express that distance in terms of A and B. So I use the Pythagorean theorem or the distance formula, really the same thing. And d of t is the square root of a squared plus, that's b squared. And our domain is just 0 to 1 because we're just looking at the time from 7 p.m. to 8 p.m. So we do have a closed interval here. So now we're going to minimize that distance in terms of time. So to find the critical values of this, after simplifying it a little bit underneath the square root, I find the derivative. And then I want to find the zeros of that derivative for the critical values. And the zeros just occur where the numerator is 0. So I set this numerator equal to 0 and solve. I get 9/25. So now, since this is a closed interval, I need to check my endpoints as well as the value of d at the critical time, 9/25. So if we check the endpoints at time 0, which is 7 p.m., we know that B is 15 kilometers from the dock, and boat A is at the dock still, so they're 15 kilometers apart. At 1 hour, we know that boat A is 20 kilometers from the dock, and boat B is at the dock, so they're 20 kilometers apart. And when t is 9/25, when we put that into our distance function, we get 12 kilometers, and that's the minimum value. So then if I convert 9/25 of an hour to minutes, I get 21.6 minutes after 7 o'clock. The distance between them is minimized. And this is that distance function. And here you can see, this is in T's in hours. Here you can see that minimum value.